This video is presented to you by Physics for Students. To know more, please visit us at physicsforstudents.com.
Okay, so welcome to yet another episode of Einstein's field equations, and today we are going to discuss about metric tensor, which is also called a fundamental tensor. This is important in the Einstein field equations. So before we start, let us quickly look on the topics that we are covering. So first we need to know what is the need, or why do we really need a metric tensor. So where does the need arise? We are also going to look into tangent vectors, tangent bundles, and tangent space. We are not going to look into a mathematical part too much into all those things. We are just going to touch base those things which are required in order to understand metric tensor. Okay, this is the third point, a measure for measure. No, it is not the Shakespeare's play. We are just going to see, well, let's skip it as a surprise. Components of metric tensor, how it behaves in different coordinate systems, a rubber sheet analogy, metric tensor, how it is related to gravitation, symmetric nature of metric tensor, physical meaning, and the mathematics behind the metric tensor. So more or less these are the topics that we are going to cover. Okay, one thing is quite important before we plunge deep into the pool of metric tensor is that this is my YouTube video playlist link from Physics for Students. So if you have not seen any videos on tensor so far, I would strongly recommend you to go to Physics for Student playlists and find out tensor analysis. You will find a couple of important videos on tensor. Although if you don't know tensor at all, or you have not gone through the mathematical details of tensor, not a problem. This video is self-sufficient enough in order to make you know about what is a metric tensor. But still, I would recommend you to go and have a look into tensor, because it covers a lot of transformation, coordinate transformation, change of bases, the Einstein tensor, all those things. So in case you really need and you feel at any point of time the tensor is important, you are welcome. Go there, check out, and you can find the further details. So we are going to take a twofold approach, as I do in most of my videos. First one would be illustrative and intuitive. You can tell more or less this is a non-mathematical background where we will use figures and illustrations to make you understand. And the second one would be mathematical background, which will give you a kind of a better understanding, a solid understanding of metric tensor. Okay, so before we start, I would like to recap what we left in the where we left in the last video, and also for viewers this is important. So we will start with the components of Einstein field equation and see what we have already covered. So this we all know, this is the Einstein's famous field equations. We call it EFE in an abbreviated form. This is the Ricci curvature tensor. This R is the Ricci curvature scalar. G mu nu is the metric tensor, which we are going to cover in this video. We have got lambda, which is called the cosmological constant. We have got capital G, which is the good old Newton's gravitational constant, and we have got C, which is the speed of light, and the last component T mu nu, which is called the stress energy momentum tensor. So we are going to cover G mu nu, which I have circled in red, which is the metric tensor. Most of these things are not most of the things, I would say Ricci curvature tensors, Ricci curvature scalar, stress energy, more or less is covered in this video. So you can just have a look and go to the Einstein field equation playlist and you can find out this video. This is quite a comprehensive and an easy understanding on Ricci tensor, Ricci scalar, stress energy momentum tensor, and what is the Einstein tensor. So if you really want to know that what these components are, what they behave, and the internals, you can go back to this video which I am showing right now in front of your screen and check it out. However, we would be going forward and understanding about the metric tensor in this video. Okay, so as you see, metric tensor comprises of two words. One is metric and the second one is tensor. Now, if we look into the generic meaning of metric, I mean to say, for example, as a language student, you go and refer to some books or dictionaries. Metric generally means measurement or meter. So it refers to some kind of measuring. It can be measuring distance, it can be measuring success, it can be measuring weight, whatever. But it some way pertains or relates something to measurement. So this is actually what metric is all about in general. So we will build up slowly on further meaning, but this is what we know metric as of today if we are a non-mathematical student. Well, tensor is something which is a mathematical objects, array of components, various other things. So let us understand that tensor is a mathematical object, right? It behaves in a special manner and it obeys certain laws. Okay, some mathematical object that brings together different components, their coordinates obey certain rules or laws of transformation under the change of basis. Now these words, rules and transformation, change of basis, if this is not sounding clear to you, don't worry, we will make things clear. You can refer to my earlier videos as I told in tensor. So let us understand in this way that tensor is something special which relates to components, their changes with a certain specific rules. Now I told just now their coordinates obey certain rules or laws. Now why we call coordinate transformation, it will become clear, because general theory of relativity is related to transformation from one system to another, right? This will become clearer. So there is a relation between metric and tensor, and here is a funny figure. So we are thinking, okay, what is the relation between metric and tensor, which we are discovering slowly. Now one thing I would like to keep a note over here is that most of the online stuffs and the writings etc., where people claim that explaining tensor in a layman's language, this is wrong. There is one concept that tensors are not generalizations of vectors and matrices. Okay, I'm not going to tell you why, because this will again take a lot of time. So let us just understand that tensors are not this, because it is slightly more understandable, it is slightly more easier to understand. That is why we use the notion that tensors are generalization of vectors and matrices etc. For example, if I give you something like this, if we say that vanilla ice cream is a generalization of chocolate ice cream, it is easy to understand, right? Than to say vanilla ice cream is a generalization of a dessert, right? So vanilla and chocolate both are ice creams, but chocolate is not equal to vanilla. So let us be aware, right? So let us not go, or rather let us not understand this false that it is tensors are generalized notions of vectors and matrices. No, it is absolutely not. Just like vectors are not only arrows, we show vectors with arrows, right? On the right hand side it goes the tip to tail, the addition and all those things. Tensors like that, like vectors are not only arrows, so which we do conventionally. So we do conventionally also tensors are generalizations of vectors, they are not, right? So just as vectors are not like arrows, tensors are also not generalization of vectors and matrices, right? So we can tell in this way for our understanding that it is a concise mathematical framework and it obeys transformation rules, so it obeys certain set of rules. So now if you ask me, I would say technically that we can say tensors as multilinear map from a vector space to a scalar field. Okay, so that is what tensor, if I want to frame it in a word or a line, which is equally difficult to do. So it is a multilinear map. For the time being, let us understand tensors to be transformation using coincide mathematical framework in some special way, which we are yet to discover. Okay, now the question is that why do we need a metric tensor? Now when I say why do we need to go a little bit back onto the history of mathematics, or the history of development of tensor. Now you see, I have shown here a figure, Albert Einstein sitting in the middle with some of his friends. If you can identify on the left hand side of Einstein, this red mark, this is his friend Marcel Grossman. Okay, now if you have seen my earlier video, which is called The Architects of General Theory of Relativity, I have actually shown that the concept of tensor was not with Einstein, but rather with his friends Marcel Grossman and Michel Besso. Okay, don't take me wrong that I'm going to undermine the talent of Albert Einstein. Obviously, I am nowhere, and he is indeed one of the greatest physicists ever lived on the surface of Earth. But what I'm trying to tell you is that the concept of tensor was known and developed by some scientists and mathematicians independently. And Albert Einstein, as I call him, a great synthesizer, actually took those concepts and developed. Why? Because Einstein's gravity is with the curvature of space-time, and Riemannian geometry deals with curvature, right? So here I say Marcel Grossman, who was Einstein's friend and classmate at Zurich, and he dealt with differential geometry and tensor. If you see my earlier video, you will see that I have shown certain writings of Marcel Grossman where he is introducing the concept of tensor to Einstein. So what is the need of tensor, metric tensor? It is because his theory of gravity deals with curvature of space-time. And curvature of space-time, or curvature of space during that time, was only handled by tensor, which is a part of differential geometry. And these two gentlemen, which they are right at the bottom of your screen, one is Tullio Levi-Civita and Gregorio Ricci-Curbastro, they independently developed the concept of tensor. We will see how Tullio Levi-Civita's connection with Gregorio Ricci-Curbastro actually helps Einstein for a better understanding through mathematical equations. So you can also look over a book which is called Einstein's Italian Connection. It's a nice book, right? So what I mean to say is that Levi-Civita and Ricci-Curbastro, along with Marcel Grossman and Michel Besso, they knew about the concept of tensor, and they introduced so that Einsteins get an easier help to deal with curvature of space-time. So that is basically the need of metric tensor. They were independently developing the concept of tensor, which later came to Einstein, and Einstein took this concept up. Okay, now if we take a kind of a flat surface and try to draw a line, it will be something like this. Okay, and if you take a curved surface, just an arbitrary curved surface, and if you draw a line, then it will look something like this. Okay, now what I mean to tell is that, say for example, tensors are multi-dimensional array, so it goes from 1, 2, 3 up to n, right? So what I can tell from this is this is a tensor which forms a multi-dimensional array. So 1, 2, 3, 4 up to n with respect to a specific basis. Now what I called basis, this is a multi-dimensional array. So you can look into basis, more details into my videos in tensor. So this is a basis, say for example bi, and this basis changes in this way, sometimes in this way, and sometimes in this way, right? So when the basis is changing, the tensor is also changing, right? Now what is basis change? We will come to that later, but as the basis changes, that means there is some change in the coordinate or the arrows, the tensor behaves exactly in that way. So I can tell that this allows us to define tensors as objects adhering to the transformational behavior, right? An object which sticks, which adheres to the transformational behavior. So we can tell that tensor can be thought as a device which makes corrections to the Pythagoras' theorem when the right-angled triangle on a curved space is drawn instead of a flat space. So it's a kind of a correction tool. Why I tell correction? Because once you draw a figure on a Euclidean plane, it won't be the same in the curved surface. So you see there on your screen, the line has gone different in the curved surface. So what is the correction? That is what metric tensor does. Just a very gross understanding. Now, as we all know, the central idea behind general theory of relativity is curvature, right? So if I get a plane something like this where we got points 3, 2 and 5 and 6. So how do we compute the length? Simple, we do this, and we get a approximate value. So this is a simple formula we have used, I think, in our school days to compute the length, right? Now if I get a surface like this where this red line curves something like this equation won't hold. So I have shown a cross line. This will not be applicable over here, right? So we need to calculate these infinite small distances, and we need a metric tensor for that. So I'm building on the concept slowly so that you can get hold of that. So I can tell that metric tensor actually defines or compute length of curves on a manifold. It actually defines infinite distances on the manifold, which I called as differential lengths and the tangent vectors. So what is tangent vector? That would be the topic we will understand in the next part. Okay, so first of all, a note that we are not going to look too much into the mathematics of tangent vectors, otherwise again it will take a lot of time. We will deviate from the main topic of understanding what is a metric tensor. So let us understand that tangent vector is a vector that is tangent to a curve or a surface to a given point. The question is that why do we need it? Now, if we want to define a parametrically defined curve, it is as a derivative of dependent variable with respect to another dependent variable. We have done in our basic calculus, right? So if we get these to be the coordinates of points of the curve, and we get the first derivative as this, then we get this line, we get x and p 2 points, right? So this blue one is the curve, right? So in this figure what we do is that point x is moving at point p. As point p moves towards x, vector from x to p approaches the tangent vector at x, right? And we can recall from calculus, we know this, and we are given this. So if we calculate the unit length of tangent vector or at point f and u, we get this. And further, if x is the length of a vector x, we get this. However, if unit length direction of vector is preferred, then further we can go and get this. So this is kind of just a basic thing to let you know about what is a parametrically defined curve. We have done in our school days, so no point in describing or explaining things more. This is how it is done. Now the derivative of the parametrically defined curve x equals to xt, so we can show this. These are the derivative of parametric equations. We can get a second order, and we can get the speed of a particle. Now when we tell the speed of a particle, I mean to say the velocity of a particle is the derivative of the position function describing the particle's motion, obviously here. This is just a kind of a summary, nothing more than that, what is the derivative, the second order, and how we can get the speed of a particle. Okay. Now you see this is a curved surface, and we get a point which I marked it in red dot. And how do we calculate that? How do we calculate? So we use tangent vectors, right? So a tangent vector is a vector that is tangent to a curve or surface at a given point. Even if we get a circle, we can use this tangent vector, right? So why we need tangent vectors? Even if we get this kind of a curve 1 2 3 4, we get all those tangent vectors. So it is tangent to a curve or a surface at a given point, and because it is curved, we are using this. Why we are using this is general theory of relativity is full of curvature, right? So you understand, in order to calculate the curvature, in order to go forward for further calculations, we need tangent vectors, and that is why we are using this. Okay, now we come to the concept of tangent bundle. So if you just imagine and think, what is a bundle? In general, bundle means say a bundle of stick or a bundle of commodities, etc. So when we talk bundle, it is basically collection or assembles. It accumulates or it takes together certain things, right? So which collects or assembles all the tangent vectors. Okay, so if this I consider to be a space, anything, just this is a space, right? Let us think as to be a space, a holder, something which is holding all the vectors, and let it call M. Just for the reason, I know that you might be imagining M as a manifold, but let us imagine M, right? And we call M as differentiable manifold. Don't worry, we are going to explain what is a differentiable manifold. So what happens is all these orange lines, these vectors, right, these are actually passing through this. So all these are bundles, right? which assembles all the vectors. Now tangent bundles, fiber bundles, all separate topics, we are not going to look into that. So these are examples of several tangent bundles. You see that a cylinder, kind of a bigger cylinder, and a circle and a manifold. So what we need to understand is that this tangent bundle occurs on a differentiable manifold, right? This is occurring on a differentiable manifold, just to give you a visual understanding. Now when I talk of differential manifolds, something like this comes to our mind. This is a surface, right? These are lines going up, horizontal, vertical, right? So what is a manifold? We can tell here it is something where we can perform differential calculus. Okay, we can perform differential calculus. So for example, these lines, these red lines which I have shown, that means we are trying to measure some kind of a distance, okay, infinitesimal small distances, differential distances, right? So we can calculate that, and now we call a differential or a differentiable manifold is a topological manifold which has a differentiable structure. So a manifold which has a differentiable structure, and that means a structure on which we can perform differential calculus. So you see all those D's on the left hand side of the figure. That means we have got something where we can use our familiar dy dx in order to do the calculus, right? Now if we want to define what is a differentiable structure, I can define like this. A differentiable structure on a set M makes into an n-dimensional differentiable manifold on which we can do differential calculus, right? So a differentiable manifold is on a differentiable structure and on which we can perform calculus or differential calculus. It is basically the differentiable manifold, and on this manifold all these vectors bundles are there, right? So it is clear, the vectors to the vector bundle on a differentiable manifold where we can perform the differential calculus. Okay, let us keep this figure on the left hand side so that it gives a kind of a visual representation. So now if we take something like this, a tangent bundle on a differentiable manifold M, and you know now what is a differentiable manifold, is a manifold Tm which assembles all the vectors in M. That is the manifold or the space where all these vectors are, right? So we can define tangent bundles is the disjoint union of the tangent spaces. I hope we all know what is a disjoint union. Just let me show you technically how we can do this. So we are using Tm equals to this which is called a coproduct. So I would like to tell you that we are using the coproduct as it includes the disjoint union of sets and topological spaces, right? And we know what is a disjoint set. So disjoint sets are those whose intersection with each other results in a void or a null set, and disjoint union is the coproduct in category of set. So it is a binary operator and it combines all the distinct elements of a pair of given sets and retains the original set. So we get this and we get this and we get this, right? You doing the union. This is quite clear. So just to tell you, this one which is on the left hand side, red underline, this is tangent space to M, and now you can understand why we need those tangent in order to know the curve, why we need these curves, because general relativity is all about curve. And X, this one which is includes M, is a point. So this is a more or less a technical definition where things become much more clearer. Tangent bundle. So now for example, if we call of a tangent space, again we will just touch base on that. So if we have got a sphere, a nice sphere, okay, and we have got a point which is X, I just underlined in red, okay, all the tangent vectors, these are the tangent vectors, right? All the tangent vectors, or rather we can tell the set of all tangent vectors of manifold M, okay, this one is the manifold M, forms a tangent space, and the disjoint union of all tangent spaces on a manifold forms a tangent bundle. So if I get so the set of all tangent vectors at a point X, which is on the left hand side of your screen, forms a tangent space T sub X M. Now in order to give you a better idea, I have drawn another figure, right? I've taken it from internet, right? So these are actually, so you see 1, 2 and 3, these are the tangent vectors, right? So we can tell collection of all tangent vectors to a manifold at a given point, here it is X. Right, so intuitively you can tell that it contains all possible directions in which one can tangentially pass through this point x. The elements of the tangent space are tangent vectors. Okay, for a sphere, this one, I can draw something like this. So for a sphere, you can imagine the tangent space at a point as the plane that just touches, I would say just kisses the sphere. It is perpendicular to the sphere's radius. So the tangent space at a point on the plane which just kisses the sphere, and it is perpendicular. So this actually gives you a clear concept. What is a tangent space? That's it. Okay, now let us summarize. It is better always to summarize what we learned together right now. So we got an Euclidean plane, and then we moved into non-Euclidean plane where the equations do not hold, right? And then we got to curved surfaces. Why? Because GR relates to curved surfaces. And for the curved surfaces, for the measurement, we need a tangent. From there we got a tool to measure these distances, which is a metric tensor. And we also got tangent vectors and tangent spaces. You see, on the metric tensor I have given a right arrow. Okay, why? Because we will see that these tangent vectors actually gets inside the metric tensor. We will see that. So from metric tensor we move into tangent vectors, and we know a little bit about tangent space. Okay, so far so good. So we have got our metric tensor, which is dancing right now in front of your screen. So in general relativity, everything is a curve, right? So we have to deal with tangent vectors. So we can say tangent vectors, you see, I just told in the last slide, it goes inside, and what comes outside is a real number scalar. Okay, so the metric tensor you can imagine as a function which takes the tangent vectors as input at a surface or a manifold, and it produces this, which is a real number scalar. So this is overall till now the function of a metric tensor. So here is a summary. It generalizes the property of Euclidean space. Obviously it is a bigger thing than normal Euclidean space. We are generalizing. Now, you know, once I tell about generalizing, one thing comes to my mind is that we are all advancing and moving ahead, right? Newtonian limitations, then we come to Einstein, then we come to relativity, then we are moving into string theory. So we are generalizing so that in one particular theory or one particular equation, all the explanations are given, right? So that is why we call generalization. It is becoming more broader, right? If a manifold is equipped with positive definite metric tensor, it is called a Riemannian manifold, which we are not touching in this video. On a Riemannian manifold, the curve connecting 2 points, which has got the smallest length, is called a geodesic. So these are the 3 points which till now we can call of summarizing a metric tensor. Okay, this is the measure for measure which I kept you as a surprise, not the Shakespeare's play but something different. Okay, so we take $1 as a standard benchmark for measuring something. Okay, so $1 for whatever be the price, let us take it as a kind of a unit, what I would call a unit price. Let us take it $1. Okay, so we take it as just kind of a unit price, right? Now if I take this $1 in Indian currency, it stands as per the currency rate 73.52 Indian rupees. If I take a Japanese yen, it comes to this, and Thai baht, it comes to this. Now these are all metrics. The price of the dollar as it changes according to the countries that change is because all these countries have different metric of measurement. So the dollar price changes in India, Japan and Thailand. So because we have got different metrics, we have got different prices, we have got different standards of living, we have different income level, we have different prices of commodity, right? We do not have something uniform, right? So the dollar prices changes as per the country, and this is why, because we have different metrics of measurement for the country. So this is a kind of a intuitive understanding what is a metric. Now if I start walking from here and I want to reach my home, which is here, what I would do straight and go to reach my home, right? So obviously I cannot penetrate through the banks and the buildings, etc., but I can take a kind of a straight line. So I call this as G, which is a metric tensor. I call as distance Euclid, because you're using a Euclidean geometry, which is quite a straight one. Okay. Now if I want to hire a taxi or a cab, and I've got a pond in front of me, what I will do, the taxi is going to take a round trip until it reaches home, and we call this as G taxi. Okay, so what I'm trying to tell you that this one, the straight line and the curved line, both of them have got the shortest distance, but yet they are not the same. Why? Because they use different metric. The metric of me walking directly to the home is not the metric which the taxi takes round the pond and reaches my home. Right. However, I would like to tell you that I don't have a pond around my home. Okay, so this is a notion which will give you an understanding about different metrics or the measurement of distance. So now, say for example, if I want to let me go back. If I want to define this one, this white screen that you are seeing on your screen, on tablet or your laptop, whatever desktop. So if I want to define, I get 2 points and I join them, right? And I call back from many years back a person whose name is Pythagoras, Ionian, and I tell that we compute the distance something like this, right? So given a point on the screen, we can get the geometry of the screen. We can get the geometry, right, which looks something like this. Now this measures the differential distance. Obviously we are using D. Now if I get a kind of a crazy curve like this, and I get 2 points, and my line goes like this, so would we be able to use the same formula? No, because this is curved, and we get a kind of a calculation like this, which is we called a quadratic equation, because it takes something like this, like squared and then 2 coefficient and this again a square. So this is a quadratic form. So this we will explain later what it is. This is something which explains the measuring of the differential distance not in a Euclidean plane using Pythagoras' theorem, but in a curved surface where the line actually is a curve. Right. Now what is this dx and dy all about? Okay, this dx and dy actually tells that the lines are not perpendicular to each other. Right, these lines are actually not perpendicular to each other. That is why, and you can see why these lines are perpendicular to not perpendicular to each other. This is actually the notion of dx dy. And what is this g tells? This is the amount of spread. Now what is this spread? Let me show you in another slide. So g tells you the amount of spread of the curve. Okay, what I mean by spread is this. So you've got a nice pair of lines, okay, and this is how it is, and then we get another pair of lines, this. Okay, so this is much more yeah, so you see the distance between the right hand side is more rather than this one. So I tell that it is much denser, right, and this is loose, right, it has got gaps. So when I talk of say for example spread, I mean that where the curve is much dense and where it is loose, right? So what happens is that this g which we are talking about, it tells that where actually you are. So the general curvilinear coordinate dx dy means they are not perpendicular, right, and it tells you about the spread, right, and this g actually depends on where you are. So if you're on the top, it is some kind of a g. If you're at the bottom, so things will change where it is, and it has 3 functions of position which we have seen in the earlier equation. We will explore more. So this is a much denser curve, this is a loose curve. Where you are on the top, on the right, you are bent wherever in the curve. So this g actually depends on where you are, and it has got 3 functions. So what are straight lines? The laptop is straight, we have got planes are straight, cones are more or less straight, but something crazy is going on the tip. Spheres are not straight, they are curved. Cylinders are straight lines, right? Straight, I would say. So what I can tell is that I can tell you in one word that curvature is the obstruction to flatten out the coordinates surface. Right? I learned it from Professor Susskind, so I would like to repeat it. How will you know that a surface is curved or not? So curvature is the obstruction to flatten out the coordinate surfaces. So this is what is spread meant, and this is how G behaves depending upon the position. Right, and you see this G is the metric. So I have shown it in this green one. This is the metric. Okay, these are simple equations. So in one dimension it looks like this, two dimension it looks like this, and higher dimensions and further in Euclidean metric. So I'm not going to explain it further. You can just pause and take a note of this. I think this is quite clear, all those equations. And in Euclidean space, this sphere of radius 1 and radius 2, hyperbolic space, generalized Pythagorean theorem, and a flat space time. Right. So these are just equations, just to let you know, because we are moving from Euclidean to non-Euclidean, how the equations would be changing. Okay. Now we can use the Pythagoras's the same equation in order to calculate the arc length. Okay, I am not going to tell you much more about that, because you already know. So let us imagine this kind of a figure, and this ds is the differential element, and this blue one is the tangent to the curve, right? And the length ds can be calculated, so like this. So for y equals to fx, I can take so this one, and for y equal to fx, if I take x to be an independent variable, we use x as independent, so we get this. Okay, what we do next, we all know, we determine the limits of integration to find out the length. So these are the limits of integration, and we do the integration and we can find out this. Okay, so this is just to show you that the arc length calculation can be done using the same Pythagoras' theorem. It is just a kind of a quick notion. It is a kind of a quick notion to tell you how we can use this formula. Okay, now we come to the next most important part, that the components of metric tensor in different coordinate system. So I hope now it is clear to you that why we need different coordinate systems, because we are moving from one coordinate system to the another. Okay, this will become much more clearer. So we tell that the contravariant and the covariant components, they have more or less the same component in the Cartesian, which is not in a non-Cartesian coordinate system or a non-Euclidean geometry. This is something we already know, that contra and covariant for a Cartesian is the same, for the non-Cartesian is not the same. But the question is that can we prove it? Can we show it with simple examples? Okay. So you see now the definition of metric tensor right now is the components of metric tensor in a coordinate basis, whatever basis that we select, take on the form of a symmetric matrix whose entries transform covariantly. So the entries transform covariantly. It takes contravariant, which is the left hand side arrow, and it converts to covariant under the changes of the coordinate system. That means from Euclidean we are moving to whatever ABC coordinate, spherical, polar, whatever, so it will change it. And this is why the metric tensor is a covariant metric tensor. That is why we call it as a covariant metric tensor. Things will become clearer. Let me show you. So how do we define a contravariant metric tensor? We take the g mu nu, that is the cofactor of g mu nu, and then we divide it by the determinant of that. Let us see an example. So covariant metric tensor we know in Cartesian is this. Okay, so what do we do? First we take g11, that is the first component of the diagonal of the metric tensor, and we take what? They take the cofactor, which we already know by blinding those, and the value comes to 1. You can calculate on your own about cofactor. And this one, you see the red arrow, so 1 is calculated, this is 1, right? We can further using this formula calculate g11, g12, g13, and so on. So this derivation, you see the values at 1, 0, 0, 0, 0, 0, 0, 1, right? Now if I plot it, you will see this 1, 0, 0, 0, 1, 0, and 0, 0, 1. Aren't they the same? You see the beauty of calculation, right? So now you can understand that why we really don't care about Euclidean metric tensor, because it is all the same. So this green tick actually shows the left hand side g mu nu is the same what we derived. It is all the same, right? Now the question is that it is not the same in case of other coordinates. So the value of covariant metric tensor, I have taken an example of a spherical polar coordinate, right? So for the spherical polar coordinate, the metric tensor is this. So what we do, we find the values in the contravariant metric tensor, right? So first we found the determinant. We do the same thing of g mu nu. We take the cofactor and we divide it by the determinant, which gives this value. It cancels out to be 1, and this is 0, 0, 0, and so on. Now you notice when I plot these values, it shows this, which is on the right hand side. And do you notice something wonderful? This is actually a conjugate of this one, isn't it? It is actually a conjugate of this one. So, and the conjugate factors are this one, which gets conjugated, right, and this one, which gets conjugated. So let me just draw the points once more. So this is a conjugate of this. That means what? That means we have found out that the covariant metric tensor in the spherical or polar, or you can do further coordinates, it is not the same. It is either a conjugate or whatever. We are just telling this. So the point of concern is that why do we really concern about the other coordinates, the covariant or the components, because they are not the same, and you can see that we have derived not to be the same. So what we can take a conclusion from here is this, right? So what we can tell right now is that the contravariant metric tensor is a conjugate of a covariant metric tensor, right? So a contravariant metric tensor is a kind of a it is a conjugate of a covariant metric tensor. So this one, g mu nu on the top, is a conjugate of the covariant metric tensor, and that is why you see in Euclidean and Cartesian coordinate system the metric tensor and its components are the same. In other coordinates systems they are not the same. So I hope you got hold of this simple nice derivation why we really care about the non-Cartesian system, because it is not the same. Okay, now we come to our analogy which we call rubber sheet analogy. Now just a note of caution to the viewers, this is not a rigorous mathematical derivation. This is a kind of an intuitive understanding in order to make you understand that okay fine, this is how we understand things, this is how more or less things are. But again, this is not correct, this is not right, this is just an analogy, it is just a kind of a intuitive understanding. So that is a kind note. Okay, so if we get a rubber sheet, now let us imagine this to be a rubber sheet, and we get a straight line and we measure the distance using Pythagoras' theorem. Now say for example, what if I expand the x factor or the x coordinate of this rubber sheet twice, right? This one expands, so we can just use this formula. This is just an intuitive understanding, just remember that. So we make 2dx squared because the x part is expanded. What if both the coordinates x and y, both of them have got increased? So we will use this kind of a formula, isn't it? So we use this. So this is extended and then again extended in both the coordinates, both x and y. Now say for example, if we stretch that rubber sheet, I have to use a different figure, I'm sorry for that, because I cannot really show that grid into a stretched one. So if I stretch this one, then the line would be like this, right? It won't be a straight line. Okay, now if I get this kind of a crazy set of coordinates, right, and if I get certain points on this, okay, then what will happen, that we have already introduced this or this, we will explain that this equation will explain the distance between points. So this is going to explain the distance between these 2 points, right? So this is how actually things would be. So what I'm trying to tell you is that, so the unstretched part, okay, the unstretched portion means which carries 1 0 0 1 etc., right? This unstretched part will have those coordinates 1 0 0 1 because these are the same, right? And this can be computed using Pythagoras' theorem. But this G11 and G12, whatever these values are, this will be containing the stretching information, right? So you get this point. This is actually the stretched information which is out there, and the stretched portion, the stretched portion, the stretching information is there, while the unstretched portion is taken into the Cartesian coordinates, which is 0 1, and we have just derived that it carries value which is the same one, and we really don't care about. And because for polar and other coordinates we have seen these values are something different, that is why we need to do that, and we get the value of G as containing the stretching information. So this actually gives you a kind of a nice analogy which I called rubber sheet analogy in order to understand how things are. Okay. So this G11 which we got gets further expanded into this, right? So okay, let me tell you that let me just go back to this part. So I would just like to tell you one point. When it is stretched in random direction, the arrow, what we get, this equations becomes valid, right? So the unstretched, the whole information of stretching information is captured in this G. Okay, so let's go back to what we are. So this gets expanded to this. This is originally actually the metric tensor of general theory of relativity. So the tensor actually stores information, right? And these coordinates, okay, let me show you this animation. These are the lines, okay? So if we know that how much and in which direction the sheet is stretched, for example, the right hand side corner, the black one, right, we can easily calculate the distance, and here comes the metric. This calculation of distance is stored in G, which is stored in the tensor, right? So we get different. So yeah, so how much and in which direction space-time is stretched, how much and in which direction space-time is being stretched, that is captured by G. So we get rank 0 tensor, you can call it as a scalar. So rank 1 is a vector, rank 2 is a matrix, and Einstein actually used rank 4 tensor, this one, in order to store the information of space-time. Intuitively, don't take me wrong, that you can think of rank 4 tensor as 4, and the 4 dimensions of space-time, length, breadth, height and time, 4 multiplied by 4 equals to 16, and that is why in Einstein field equation we get 16 partial differential equations, or I would say 16 partial non-linear curved differential equations. So 4 multiplied by 4, 16, that is why I get 16 differential equations. Okay, now we will come to a concept which is called a mapping. This is important. Again, this is an analogy, not a strict mathematical description. Okay, so if we get a sphere like this and we draw a line which goes something like this, right? So how do we measure this line? Okay, let me magnify this sphere into this one, a bigger one. Okay, now see what we do. We get this rubber sheet, okay, which is a unstretched rubber sheet, and we have got a straight line, right? Now what I will do, I will put this rubber sheet over here, I will put another patch over here, I will put another patch over here, and I will measure the lines over here. And then what I will do is that I will take out, this is a stretched rubber sheet, right, which is on the sphere. This is the unstretched one. Now I will take out that stretched rubber sheet from the sphere and make it an unstretched rubber sheet. So what would happen is that as soon as it is unstretched, I can use Pythagoras or differential equation in order to calculate those dy and dx. isn't it? So I can approximate any complex surface by stretching the rubber sheet, which is called a deformable Euclidean space. So every patch that you see on this sphere actually has a stretching information, which is the metric tensor. So if I know the stretching information, I can compute the distance, which is this one, and that is why we can compute the distance between 2 points on any kind of a curved or a complex manifold, right? We're using this equation. Okay, so let me just go back again once more to this. So what I try to do is that I try to map the sphere with my unstretched rubber sheet, putting out there, drawing a line, getting it out, and again trying to do the calculations, which is the G part, and the G part stores the stretching information, and we can compute the distance. So this is called mapping from one coordinate to another coordinate. From the unstretched Cartesian coordinate, I am putting it into the stretched Cartesian coordinate, and this is how things happen. So this is a concept of mapping. So what we tell that if I know the stretching information of all those complex manifolds or surfaces, we can calculate the distance, obviously how much it is stretched and in which direction. We can also know that this entire stretching information is stored in the metric, right? And this metric tensor helps us to understand those coordinates and measure them, and the tensor itself, as I told you, is a nice coin-sized mathematical framework which obeys certain rules. That means the transformation of the coordinate from one place to the other actually is there. It is all over here. So the tensor stores it, the transformational the values, and if I know them, then we can calculate any complex manifolds. So how does it help? So we know all those manifolds, big calculations, G, but how does it actually practically help it out? Now I have given just kind of an intuitive understanding. I take Jupiter, I take Earth, and I take Mercury. Okay, so because Jupiter is heavy, the curvature would be this. The Earth is lighter than Jupiter. The red line actually shows that the curvature is more, and that is why it is heavy. You see the weight, and this G obviously is not the gravitational acceleration, it is the gravitational acceleration, it is not the metric tensor, right? For Earth, the curve is this, and why I draw the red line? Because the curvature is less compared to Jupiter, and obviously the mass of Earth and the gravitational acceleration is lesser than Jupiter. I take Mercury and I draw a line like this, and I see that this red line is even lesser because the weight of Mercury and the gravitational acceleration. This actually is the information which is stored in the metric tensor G. Okay, so the heavier the Jupiter or heavier the planet or any object is, the more will be the curvature. The more will be the curvature, the more will be the I would say the weight, etc. So now you see that the heavier the object, the more curve it is, and that is why actually defines the space-time curvature, which is gravity, which is the beauty of Einstein's field equation. That so now you can tell that if Jupiter is this much curved compared to Earth or Mercury, then if a line passes through the tangentially around this line or that, and the planets or the moons rotating around Jupiter would have this axis, that all because of general theory of relativity. Because what we are doing is that we are calculating the curvature, the stretch, the dent, everything. Right, so this is a kind of an I would say an understanding which will make you understand that okay, so this is how metric tensor behaves, the curvature behaves, and that is why if you know as I told you earlier, if you know where we are and how much it is stretched, we can calculate the distances. So this is a kind of a analogy that these are the planets which have got this kind of a mass, so this is this bend, and based on that what I can do, I can calculate, I can shoot out missiles or whatever we want. Okay, so yeah, this one is the I'm so sorry, This one is the general relativity curvature. Now you see all these curved lines which we just saw here, the sphere and this one curvature, these are related to topology. Okay, topology, I mean to say the study of surface. It is a totally different branch, but this topology, why it is, because this relates to the surface, and topology deals with manifolds, and that is why it relates to general relativity. So what I tried to show you over here is that the study of surfaces are the science which is called the topology or the mathematical discipline, and because the topology deals with curvature, etc., that is why this tensor, which was developed by Ricci Kurbastro and Tullio Levi-Civita, these were actually topology and differential geometry. And because general relativity deals with differential geometry and the curvature and the dents, etc., that is why topology is intrinsically related to general relativity. You cannot say this is different from that. Maybe you don't need to be a topologist to understand general relativity, but yes, these are related. Topology to manifolds and general relativity. This is just to show you how interconnected these things are. So the surfaces to general relativity and the physics. So you can call this metric tensor is a way of measuring. Right. So this is something, we got a Minkowski metric, we got an R3 Euclidean metric, and we got a Schwarzschild metric. So why I'm showing this? Because if we have different measurements, we have different metrics. So a metric tensor depends on which plane you are. Schwarzschild metric won't be the same as Minkowski or a polar coordinate. So it depends on how things are. Okay, so we remember that every point in a coordinate system has its own vector space. Every vector space has its own metric, and this metric enables us to compute distance, angle, and volume. This is just a kind of a nice recap. So this is called the Euclidean. So we have, even now you can relate that this is exactly the same in all part, because we have calculated this, and this is the unstretched, like the unstretched rubber sheet. So the stretched rubber sheet would look something like this. This is just to give you an understanding how these two metrics are different. Okay, now this is something important, but I would like to tell you that this actually calls for another subject. This is a very important and intricate subject, that whether metric tensor defines gravity or not. Now the answer is yes. In general relativity, a gravitational field is a result of the curvature of space-time. And actually this metric tensor shows the metric conditions and the gravitational field relatively to an arbitrarily chosen system of coordinates. Why arbitrary? Obviously because it is curved. We don't know what system it is. So the geometrical properties of space-time with its metric are defined by physical phenomena, right? They are not invariable properties of space and time. So we should note that this one, which we will see what it is later, this has got G as the metric tensor, right? And these are the components of metric tensor. We will show you what these things are. And these components actually plays an inevitable role in gravitational potential. So the components of metric tensor plays an important role in the invariance through which the matter establishes these components are given by the Einstein field equation. Now, just a point of note that we need to understand is that, see, when we develop a kind of a theory like general relativity or any kind of a mathematical or a physics theory, right, when it is generalized, does that mean that it encompasses or it encapsulates the earlier Newtonian theory? Well, in some way, yes. Because if you are discovering a theory or a formula, this would obviously encapsulate the lower, I mean to say not lower, the earlier one, and that is why it becomes a higher formula. So can we go from general relativity to Newtonian mechanics under certain conditions, and from Newtonian mechanics can we again go back to GR? That is the question. So in general relativity, the gravitational potential is replaced by metric tensor. This calls for a separate discussion a lot of mathematical derivations. I'm not going to do. In the Newtonian limit, now you see I have written replaces Newton's gravitational potential from Poisson's equation with a tensor potential that shows the distribution of this. Now you should note that this actually happens under certain conditions. So in the Newtonian limit, when forces are less, objects are moving much slower compared to the speed of light, the gravity is not that fast, etc. So GR reduces to Newtonian gravity, and metric tensor can be expanded in the terms of gravitational potential. Okay, but remember, it is under special conditions, not always. Okay, so you see here is our favorite professor, Sir Isaac Newton, our beloved sir, and from his Newtonian equations, we have two equations. This one as the second law. This is not I would say this is not an easy derivation. Anyway, I am not showing the advanced calculus. So this is one which comes from the second law. From gravity we get this. Okay, so the second law from Newton's law of gravity, we get can be reduced into this, which is a geodesic. I got this as a research paper with some other professors. I'm not showing the derivation. Again, it will call for a separate video. So the second law gets reduced to this, which is the equation of the geodesic, and this one gets reduced to the Einstein's field equation, right, where phi is the gravitational potential, this is the nabla, is the gradient operator, and obviously a on the left hand side, I am telling, is the acceleration through space. Now you see the wonderful beauty. Now you see this we are considering in case of non-relativistic limit. That means we have got a stable, simple matter energy distribution, not much force, not much momentum, and everything is nice and fine. And this EFE, Einstein field equations, actually comes from Poisson's equation, which is this, and this is the second law. Now so we see that here you see a particle's relativistic world line can be thought of just a gravitational field which looks like a trajectory plotted through Newton's second law. This is something, right? Now you see that if this F equals to ma is being reduced to this and being reduced to this, what is happening? What is happening? Actually what is happening is that this one, the famous Newton's gravitational equation, gets reduced to this, and it gets reduced to Einstein-Field equations. What is happening? Now you see the beauty, real beauty of mathematics and science. This is related to motion, right? F equals to ma. It is related to another motion which is geodesic. Isn't it wonderful? So you see, motion is related to motion, but this motion is on a Euclidean plane, normal geometry. This is the geodesic curved geometry. Here also geodesic means the distance which a particle travels, the shortest distance. Motion is more or less that. This is an intuitive understanding, and this is what, obviously, gravity, and this relates to curvature of space-time. This the below, the bottom line on the right hand side, this is what, the curvature of space-time. This is Einstein's field equation, right? So you can just take a small snapshot if you like. So motion is being generalized to another motion which is geodesic. Gravity relates to curvature of space-time, which is also relates to gravity. So how beautiful things are. So this is how things can be reduced, obviously under special conditions, which I repeat. So I've just thought this is gravitational potential, which is replaced by metric tensor, and G00, which is the first diagonal component, is actually the phi, or the gravitational potential. So GR going to Newtonian mechanics, Newtonian mechanics going to GR. It is difficult to map, but anyway, under velocities which are low, masses are low, we can do this mathematically. Okay, so this one can be written as this or as this, right? So this is just the calculation. So with x as a point, right? So GR replaces to Newtonian gravity potential from Poisson's equation for gravity with a tensor, which is the metric tensor. We need a tensor, otherwise it won't obey the laws of transformation. Under special cases, Newton's law, gravitational potential is replaced by metric tensor. Now in the Newtonian limit, G00 component of the electric tensor actually depends on the gravitational potential, and this is obtained by simplifying Einstein's equation into non-relativistic equation, which is a Poisson's equation of geodesics. Okay, now if I say that in differential geometry you can have a curvature which is not a metric, okay, but this requires a special connection which is called the Levi-Civita connection. You remember Tullio-Levi-Civita, so this is a Levi-Civita connection, right? So this is a unique torsion-free connection. So you see I have described that this actually describes the metric and it is torsion-free. So because it is a torsion, we save the twisting part, right? So it is the tangent bundle compatible with the metric. So yeah, it saves us from the torsion problem. Now if I take M to be a smooth Riemannian manifold with a metric G, then a connection, or yeah, G is a metric, a connection on M is said to be compatible with the metric on M if this is the Levi-Civita, if this is equals to this. I'm not going to, so the left hand side is actually we are applying vector for a smooth function. This is what it shows. Okay, so this is what we know, this Levi-Civita connection, which is when applied to G. So when Levi-Civita connection, this one, is applied to G, it is completely specified that this is 0 and this is torsion free, right? So the metric describes, so G, the metric tensor, it describes what? The Levi-Civita connection, which in return completely describes which is the Riemann curvature tensor. I have deliberately ignored the indices just to avoid confusion. The Riemann curvature tensor in which the gravitational field actually manifests. So we say that the metric G describes the gravitational field. Now even if we write the original Riemann metric tensor, which looks like this, you see all those red lines, these are connections of Levi-Civita. So I hope now it is clear. The Riemann curvature tensor relates, if I go back from the right to the left, the Riemann curvature tensor relates to the Levi-Civita, which relates to the metric tensor. And Levi-Civita, because it makes torsion free, it actually describes G, and in this way they are related, right? Then when we write the Einstein field equation, the metric becomes an independent creature. It is an independent identity of the coordinate system. That is why all these are required. Okay, this is the time to take a break. You can have your coffee. I will just go and grab my coffee with a little bit of cookies because it has been a long time talking. Okay, welcome back to the break. So we are just left with the final part of our video. Now we are just going to describe the symmetric nature of the metric tensor. Okay, now if you have seen my earlier video, even if you have not seen, not a problem. Metric tensor is actually symmetric in nature. Why? Because this one gets cancelled out, this one is similar to this one is similar to this, and this goes on dot, and we get G mu nu equals to G nu mu, and that is why we call it as a symmetric tensor, right? So this mu nu relates to the 4 dimension of space and time. The 10 components of the metric tensor, we reduce this 16 to 10, and these are the 10 components, right? So this equation is still valid no matter whatever coordinate system we are selecting. Okay, now these are the 6 unique elements. I've just drawn this, don't mind my handwriting. So this is just the 6 unique elements of metric tensor. This is the same as the stress energy momentum tensor. Okay, so let us see what is the stress energy momentum tensor. Same 0 0 0 1 1 0, this gets off, and dot it goes on, and we get T mu nu equals to T nu mu. So again the symmetry is being retained. And this one, again, these are the 10 components of metric tensor, which you can further reduce, right? So the components of the metric tensor in a coordinate system basis taken on the form of a symmetric matrix whose entries transform covariantly interchange the coordinate system. Thus a metric tensor is a covariant symmetry tensor. So it is just a, I won't say duplicate, but it is another way of defining it, right? So if you now imagine the Einstein field equation, what we see on the left and what we see on the right, the curvature of space-time, which is defined by the metric, and the T mu nu, which defines the movement of matter, both of them serves the symmetry. The books are balanced. Okay, I was reading over this book of General Relativity, right? I just thought to give you a basic understanding. It's a wonderful book, and somehow regarding the symmetric nature, the author says this. Okay, and this is what he assumes. Now this actually caters to the question of symmetric nature of metric tensor. What actually it is, let us see. Suppose we take this, so alpha beta, this one is not equals to this. On computing we get this and this and this. Now you see what is done. So I have taken these two indices and I have just swapped them, right? But you see I have swapped the indices, but I have not considered the anti-symmetric part, right? So I have not established that the metric is equal to its symmetric components. Okay, right. So we take this equation forward so that it remains in front of us. So here alpha and beta survive, so we can tell this is symmetric. However, if we take this forward, we must have the symmetric nature of this one contributes to the contraction of the symmetric tensor as alpha beta, right? And that is why we call this equals to this. So now we can tell that through that we can find out the symmetric nature, right? Okay, in simple words, what we can say, this one, whatever the notation, you can take nu mu or alpha beta, this is the same as this. And why? Because the multiplication factor in the Einstein summation is the ordinary multiplication, and hence it is commutative. So this is symmetric. This is another way of saying the symmetric nature. Now there's a third way of saying it. Now this one, in order to be symmetric, we must have by definition, so this one by definition we get this one, right? G equals to within bracket G alpha beta, which comes at the below at the downstairs, right? So, and we know this is by definition, which satisfies the following conditions, and all second order partial derivatives of this one should be continuous. This is another one. This is also, it needs to be symmetric. Then what will happen is that this value should be greater than 0, and you should take into account that G is non-singular, right? G is non-singular, and that is the absolute value, and we get this, right, the differential form, and we get the distance concept, which is generated by G is invariant with the change of coordinates. Simple, clear definition why G is invariant, taking 3 instances. I think that actually clears up the concept. Okay, so let us see what is the physical meaning of the metric tensor. I mean to say physically how we can define that, right? Okay, so for the stress energy momentum tensor, in the earlier video and even now, I have categorized them individually. So this is the energy density responsible for the space-time curvature. This one is the pressure. You see the hand is crushing, so it also acts as a source of space-time curvature. This is the movement of matter, which causes energy to transport, and is called the energy flux, which causes the curvature. So energy, any part of the energy that we think in this universe somehow takes a place in this matrix. However, when we talk of this one, we have to make another video in order to explain each and every component. So I have taken Sean Carroll's this book and have just drawn a basic simple idea. It contains the stretching factor. It allows the path length to proper length to be calculated. It replaces the Newtonian gravitational field, which we have seen. It generalizes the notion of the dot product. This one again requires a mathematical thing. It determines the shortest distance between different points. So actually that clears it up. So if you want to have a note, this is overall the physical meaning of the metric tensor. Right, we now come to the last part of the video, which is called the mathematics of the metric tensor. when we talk of the mathematics of metric tensor, first of all, okay, let this be the screen, otherwise it will be blank. We need to be aware that we are doing a lot of coordinate transformation. That means from Euclidean we are moving into non-Euclidean, from unstretched to stretched, from straight line to curvilinear lines, and all those things. So what we will do is that we will take this kind of a coordinate transformation, which is a Galilean transformation, and we further take Cartesian to polar, and from polar Cartesian to spherical, right? So what we are doing is that because general relativity deals with coordinate transformation, we will follow the prime notation convention. Okay, so this is nothing that we are going to transform all those things, but this is just to show you that we generally use the prime notation convention to denote the coordinate transformation. Now, transformation from the unprimed to the prime. So if there are two coordinate systems in which linear relationship exists, transformation is quite simple. Why? Because we call the differentials of one system dx to dx prime, dy to dy prime, and dz to zz prime. So just understand that transformation from the unprimed, that is the left hand side, dx, dy and dz, right, from transformation from the unprimed to prime comes from the rule of partial differentiation. So we are transforming from the unprimed to the primed, which is quite this, goes to this and to this. So we use the index notation, and you can later do this calculation. This is from the unprimed to the primed, and we will take forward this dx primes in the next slide. Now, using this index notation, okay, that is substituting. Now, one thing I would like to, so what are these? x1, x2 and x3 we are substituting for x, y and z. These are the contravariant components, right? So these superscripts are mentioned so that you can understand that the differential length elements, they transform contravariantly, right? So taking this factor, if we calculate the earlier, it takes into this kind of a matrix, right? You can do, and I can put it in a kind of a matrix. Now I can calculate dx prime 1 by using the sigma notation. I think it is pretty simple and clear. So we are using from 1 to 2, 1 to 3, and we are summarizing or summing up in this prime, dx prime 2 and dx prime 3. So this is just a way to write and shorten up things how these are. Now these are again, this j, these are repeated. These are repeated, right? So what we do is that if I index is 1 to 3, this one, this sigma notation is being replaced by our famous Dr. Albert Einstein summation convention, which is this, right? So here what happens is that, what happens is that the j get replaced, the sigma is removed, and the equation looks nice and handsome, right? So this is using the Einstein summation convention. Now what happens is this big differential, partial differential equation gets reduced to this, and that is the beauty. Isn't it beautiful? This entire equation we can use in this way. Now if we take the index notation, this one, okay, what it tells, this one, a sub a prime I, this is primed or the transformed coordinate, right? We are moving from the unprimed to the primed. This one denotes the weighting factors. That means if we take the index notation, it tells the components of a vector in the primed or the transformed coordinate system are the weighted linear combination of the components of the same vector in the unprimed or the original coordinate system. Clear? Now if we compare this equation with this equation, what do we see? We see on the left hand side there is something like this. This is a primed value, right, with a free index I appearing. Now on the right hand side we see a dummy index, right, this one, the j part. So we represent the elements of the transformation matrix by this, right? So what has been transferred, elements of the transformation matrix for a contravariant vector is this one, and this is the elements of the transformation for the differential length elements is this one. So instead of looking this right hand side equation as simply the index notation, we can call it as a transformational equation which takes differential length elements from unprimed to the primed coordinate. So this is actually a transformational equation which takes differential length element from the unprimed to the primed coordinates. Right. Now we are dealing with the metric tensor, right? So question is that why do we need a coordinate system? We need a coordinate system so that we get a set of rules, the objects obeying certain rules, and we call it in a wrong English arithmetizing the space. We arithmetize space. That means we are drawing certain rules in which the objects in the space will behave, and we can calculate accordingly. If there is no rule, the entire thing breaks down. So we call G as the metric tensor, and we have got these things, the contravariant, covariant. So the upstairs is contra, the low stairs is covariant. We have got EI and EJ as the basis vectors. Now if we get DS as the 2 points separated by an infinitesimally small distance ds and a vector dr which extends from one point to another, right? What we got is this. The square of the differential length element can be written as this, right? Now this vector dr can be written using contravariant components and coordinate basis vector ei, which is this one, right? Or using the covariant components, we can use this, and since ds squared is the dot product of dr, which is that extended vectors with the blue arrow, we can write using contravariant component this one, this, which leads to this, and this is, you see, as the covariant component of the metric tensor. So this is how we define using the covariant component of the metric tensor, right? Okay, fine. Now we take things further. Now what we do is that we take, using the covariant components further, we can write this on both sides, which leads to this, right? And what we get is a contravariant component of the metric tensor, right? So here we have used the covariant, this one we got what? The covariant component, and now we got the contravariant component tensor. Now what if we apply both? It is called a mixed tensor. Anyway, I don't want to go into that. What if we apply both? We get this. So these red lines are using both contra and covariant. We get this and we get this. But do you notice something? We don't need a metric tensor, something G or something. Why do we don't need a metric tensor? As the definition of dual basis vectors is this, right? This is 1, and if I equals to j, and 0, and if I is not equal to 1. So here we really don't need a metric tensor because of the definition, this one. Now the most important part, do you notice this? If I take ds square as the differential length, whether we use contra, whether we use covariant, whether we use the mixed tensor, the distance between the lines are always the same, irrespective of the coordinate system that you select. And that is the beauty of metric tensor. So we are finally coming to the conclusion. So whatever the components we are using, mind it, contra to co and to mixed, and now you cannot say that you don't know. You have seen how contra and co behaves in Euclidean and non-Euclidean. The distance between the points are always the same, whatever coordinates you are selecting. Okay, so now you see the job of the metric tensor, taking the co and the contravariant components, its components, it turns to the incremental coordinate, changes expressed either in co and contra, and the distance between them remains the same. And that is why you have read in books, we call metric tensor provides the geometry of space-time. It is actually the geometry of space-time. Why? Because it takes whatever it is and gives the invariance. It makes life easy for you. You can calculate the distances, right? Now if you really want to enjoy the tensorial type behavior of metric tensor, like I mean to say how it behaves as a tensor, right? So let us consider this one. We have already seen the contravariant component, and the previous example this one, right? Sorry, I forgot to give the brackets, right? So now if I want to calculate this one, that means the ds square, this would be something which I have written in bracket. And what is this something? It is this one which leads to this one which leads to this one which leads to this. So we calculated the dx1, I mean to say using the index notation. It's clear. Now also if I calculate dx2 or dx2 square, whatever, ds square is something. What is that something? We get this from this, and again from the left hand side we go to right hand side. So we get this, right? Again we write something for the dx3, we calculate this one and we get this one and we get this one, right? So this is how things happen. Okay, so each let us go further, we will understand. Now what I do is that we put all this entire equation together. It was a big calculation. Anyway, you can later see all those things. So we put it in this way with summing up, and then if ds squared, we put this and this and this and this one. This is a huge, a long one. These are all partial derivative using the primed and unprimed, and using the partial derivative rule. One thing is important: this term, or rather I would say each term in bracket, involves partial derivatives of the transformed coordinates. Okay, I have not written all those brackets, it would be too messy. So each term in this bracket involves a partial derivative of the transformed coordinates from the original coordinates x1, x2, x3 to the primed coordinates, right? So this is what it is. Now if I assign the value, that means I'm putting these values into G, 1, 1, 2, 2 and this, we get something like this, right? You can take a note, or this is just substituting these values. Now since order of multiplication does not make any sense, because this one 1 2 1 equals to 1 2 3 1 and so on, so what we do, we substitute these values into this equation. So we are substituting these values into this equation, and ds square becomes this, right? Further simplifying, we can get this. Okay, so further simplification leads to this. Okay, and you see all these indices are being covered. You can later take a screenshot or whatever you like. So all these screenshots are being covered. All these indices are being covered. Now if I take the bottom part, right, this one, and I further simplify, what will happen? So I take this part and I further simplify, and I finally arrive at the metric tensor, right? So this is the metric tensor, which is of rank 2. So you see, you can go back again and you can see that from this we have substituted the values, and this is further simplified into this, which is a rank 2 tensor, right? Okay, so finally what we do is that, suppose in a rectangular Cartesian system we get the distance between points as this, and it is given by this. So what we get in n-dimensional space, Riemann defined the distance as this ds, right? So we take this one. I have just jumbled up, I'm sorry for this is the same equation, just jumbled up the order. So this equation finally leads to this one, provided we take ij of 1 to n, and this one again is the quadratic form. You see, it follows a certain quadratic form, and this is what is called the Riemannian metric. This is called the Riemannian metric, and this one is called the Riemannian space, V sub n. So any geometry which uses Riemannian metric system is called a Riemannian geometry. So a metric which uses Riemannian metric is called a Riemannian metric system. So I hope that makes things clear. We have seen how and what a metric tensor behaves, what things are like, and how we arrived at this. 3 things which will be due for the next video is that metric tensor is a covariant symmetric tensor of rank 2. Can we show this? The dx super I is a contravariant vector. Can we show this? And can we prove this one as invariant? Because it will be proved in the next video. Now you see, this is important because we have arrived to Gij or whatever, but can we prove that this is invariant? That means the calculation of the distance. So it will take again another video to prove it. So that's it. I means we can redefine the metric tensor as a scalar which has a killing vector and the killing vector actually preserves the symmetries in the metric space, and it maps the vectors, produces a scalar. So at every point of this video I tried to define metric tensor, and this is the final definition which I found useful. So that's it. It's a summary that we need to make up, and we really learned a lot of things. What is the basic idea? What is the need, which is coming from the history, tensor being developed independently, Einstein's friends helping him. What is the tangent space, vectors and bundles? What is a metric tensor, and what is actually, it is a measurement tool, contra and covariant, very important, and how it changes we have proved. The rubber sheet analogy, metric tensor, how it is related to gravitation, and we learned that under special conditions it can be changed, and the physical meaning of the matrix and mathematics, how it behaves. So that's all. I hope you liked my video. You can like and subscribe and put up your comments. One important note that I have also come up with a website which is called physicsforstudents.com. physicsforstudents.com. You can post your research paper, you can post articles, you can send your anything. So I have divided that into different portions. I will make a video different on that, and I'm getting good responses from theoretical physicists, mathematicians, astronomers from Russia sending pictures and writing. So if you want to contribute, please go ahead and do that. That's all from me. I hope it has been, I know it is a long video, but we have covered intuitively, mathematically, more or less the idea of what is a metric tensor. What remains is now assembling all those tools, metric tensor with Ricci scalar and Ricci curvature and stress energy momentum tensor, and can we find out the final equation. So we have left with few more topics, I think, the Poisson's equation and the lambda and the 8 pi factor, how it comes from. So we need to see on that. So this is Shaunak. I am wishing you a very happy weekend and all the best. Stay safe and stay happy. Do subscribe to my channel, like, and please let me know your comments. Goodbye and have a nice weekend.